All right, this screencast is going to talk you through Chapter 27 in the e-textbook on light. We'll look at a couple terms such as emitting, transmitting, or reflecting, all of which are behaviors or characteristics of light or light-based objects. So here's a light bulb. Light bulbs emit light. So ancient philosophers believed that light traveled from our eyes to objects when we look, rather than from the object to our eyes. Well, light has been studied for thousands of years. Ancient Greek philosophers thought light consisted of tiny particles, which could enter the eye to create a sensation of vision. It has been historically widely debated as to whether light was an actual particle or a wave. Well, light moves in straight lines, like particles, and not spreading out like waves. But light actually does spread out, and we can observe this by having light diffract through a prism. It definitely spreads out. And we can look at how white light is separated into the individual colors of 4AgBiv. So it actually does spread out like waves. It just doesn't appear that way if you don't have something to have it diffract, or in this case, refract. Einstein published a theory explaining a new revolutionary idea. According to Einstein, light consisted of particles called photons. These photons are massless bundles of concentrated electromagnetic energy. This led to Einstein's duality of light nature. Scientists now agree that light has a dual nature. It is both a particle and a wave. So the speed of light. So light has historically been a mystery. It took a series of steps to advance the world of physics to catch on to the pattern of light. Olaus Raymer first demonstrated that light travels at a fixed speed. Raymer made very careful calculations and measurements of the periods of Jupiter's moon. The innermost moon, Io, is visible through a small telescope. This allowed Raymer to carefully study the timing of the moon's orbit around Jupiter. Christian Huygens correctly interpreted this discrepancy of Raymer, though. When the Earth was further away from Jupiter, it was the light that was late, not the moon. So here's Io orbiting Jupiter, and here's the Earth orbiting the Sun. And then there was Albert Michelson, who came in and correctly and accurately determined that the speed of light was roughly 300 million meters per second, which is the same as 300,000 kilometers per second, right? There's 1,000 meters in 1 kilometer. Kilo means 1,000. And we can convert kilometers into miles, and we could say that this is 186,000 miles per second. So the electromagnetic waves, the electromagnetic spectrum here is pictured here. That mathematically, wavelength and frequency are inversely related, right? C is the speed of light equals frequency times wavelength. Multiplied by one another, they equal the speed of light. Therefore, all energies on the electromagnetic spectrum travel at c, 186,282 miles per second, in the form of photons. As frequency changes, so does the wavelength. As frequency increases, the wavelength decreases. Observe a gamma ray on the far right side of the electromagnetic spectrum. At very high frequencies, they have a very small wavelength. Observe a radio wave. Radio waves travel at the speed of light, but they are a very low frequency, a very large wavelength. But at the end of the day, the frequency times wavelength equals the speed of light. So light and transparent materials. Just as sound waves can force a second receiver into vibration, a sympathetic resonance, right? We struck a tuning fork, it sent compressional waves or pressure waves through the air, and it resonated a secondary tuning fork that was at the same natural frequency as the original one. Light can force charged particles in materials into vibration. Light is carried by an electromagnetic wave that is generated by vibrating electric charges. When light strikes matter, electrons in the matter are forced into vibration. So, right, sympathetic resonance plays out with light too. Exactly how a receiving material responds when light is shined upon it depends on the frequency of the light and the natural frequency of the electrons in the material. Visible light vibrates at a very high rate, about 100 trillion times per second, or 10 to the 14th hertz. Objects that respond to these vibrations have little inertia, so electrons have a small enough mass to vibrate that fast. Transparent objects. Light passes through materials whose atoms absorb the energy and immediately re-emit them as light. Materials that transmit light are generally transparent. Glass and water are transparent. Materials that are springy or elastic respond to more vibrations at some frequencies than others. Bells at a particular frequency, tuning forks ring at a particular frequency, tuning forks vibrate at a particular frequency, and so do the electrons, other electrons in matter. Electrons in glass, right? We can imagine them to be bound by atomic nucleus as if connected by springs. So tuning forks vibrate at particular frequencies, and so do electrons. In other words, this is what we're going to look at here. Electrons in glass have a natural frequency in the ultraviolet range. When UV light shines on glass, resonance occurs as the wave builds and maintains a large vibration between the electron and the atomic nucleus, just as a large vibration is built when pushing someone at the resonant frequency on a swing. When an atom receives energy, it quickly re-emits it to a neighboring atom with the same natural frequency. During this time, the atom makes many collisions with many other atoms and gives up its energy in the form of heat. This is why glass is not transparent to ultraviolet light. One cannot get a suntan through glass. But yet on a cold summer day, visible light can enter a car and heat the car's interior. Heat is a form of infrared energy, and this heat is what fills the car and heats up the interior. Cars can be quite warm on cold winter days. So back to glass. Glass is transparent. It's transparent to all the frequencies of visible light. In a vacuum, light travels at 300,000 kilometers per second, right? 186,000 miles per second. Light is absorbed and re-emitted from one atom to another. In this case, when light is traveling through glass, it is not traveling at the speed of light in a vacuum. It takes time to be absorbed and re-emitted within the glass itself. So light travels at different speeds through different materials. Now, if I look at light traveling, it travels at about 75% the speed of light in water. In glass, it travels at about 67% the speed of light. Yet in diamond, it travels at about 40% the speed of light in a vacuum. So when the object leaves these materials, it actually jumps right back to the speed of light in a vacuum upon entering the atmosphere or space. So here's what it's saying. It's saying that an atom that's entering glass is simply just right? These are three of many atoms. A light wave incident upon a pane of glass sets up vibrations in the atoms. Because of the time delay between absorption and re-emission, the average speed of light in glass is less than the speed of light in a vacuum. So it takes time to be absorbed and then re-emitted through each atom. So therefore it doesn't travel at the speed of light in a vacuum as it travels through different materials. Opaque materials. Here I have glass that blocks both infrared and ultraviolet, but is transparent to the frequencies of visible light. And that's how we can create a greenhouse. UV and infrared are blocked, visible light makes its way through. Materials that are not transparent are called opaque. Light does not pass through these objects. The materials actually heat up as their internal kinetic energy, right? Heat increases by these coordinated vibrations of light. When you sit in the sun for any amount of time, you warm up, much like the objects that are opaque. Metals are also opaque. Outer electrons of atoms are not bound to any particular atom. They wander around, which makes them good conductors of electricity and heat. The light hitting the surface of the metal does not spring into another atom. It bounces back. And this is why we see objects in metals as a reflection, because metals are shiny. Now, as a summary, we can look at any of the topics that we've done so far, but we're starting to apply the different types of waves in the electromagnetic spectrum. And I do want to make sure you understand that glass allows light in. And as it allows light in, this is a higher frequency, a shorter wavelength. Visible light is a shorter frequency. When this light hits something, it actually heats it up. So therefore, if this plant were inside a car, it would actually be a form of the greenhouse effect, that it would give off heat in infrared around it.